Yes, let us come to the next concept on this topic is heat transfer. Transfer of heat energy from one place to another place. That can be explained in terms of three different modes. Modes of heat transfer, okay? Modes of heat transfer. There are three different modes here. One is conduction. Second one is convection. And third one is radiation, okay? Conduction, convection and radiation are the three different modes of heat transfer. We will discuss all the three different modes in detail, okay? Now let us first consider this conduction. Conduction. So for this conduction is actually the process of transfer of heat energy from one place to another place or between two adjacent sides of a body due to temperature difference, provided the bodily movement of the particles are not exist. That means the particles will present there itself. There is no bodily movement of the particles. Such type of transfer of heat energy is called as conduction, okay? So this is the process of transfer of heat energy. It is the process of transfer of heat energy. Process of transfer of heat energy between adjacent sides of a body due to temperature difference. Without the bodily movement. Without bodily movement of the particles. That means here there is no movement of the particles of the body takes place, but the heat transfer will takes place from one place to another place of that body. So the particles of the medium or a body that will transfer heat energy from one particle to the next particle without the movement. So therefore, the heat transfer from one place to another. Best example you can consider a rod. And if you heat at one end of the rod, the heat energy will transfer from one end of the rod to another end of the rod. So you can observe one of the fact here, there is no transfer of particles will take place from one end to another end, but there is a transfer of heat energy takes place from one end of the rod to another end of the rod. The process is called as conduction, okay? Further, we can discuss more detail about this conduction by using a term called conductivity or thermal conductivity. Thermal conductivity. So, in order to explain this concept of thermal conductivity, we have to consider a rod of length L and area of cross section A that is heated. One end of the rod the temperature is Tc, the another end the temperature is say Td, okay? I can define this particular thermal conductivity law. So consider a rod of length L, uniform area of cross section, uniform area of cross section A. Let TC and TD be the temperature at the ends. Then heat flow through the rod. First one is directly proportional to temperature difference. Temperature difference at the ends. Second one, the heat flow is directly proportional to the temperature difference. That means the heat flow at is directly proportional to Tc minus Td. So because we consider a rod of length L, this is the length of the rod L. Okay. Area of cross section is A. Temperature at one end is Tc, the other end is Td. Then the heat flow from one end of the rod to the another end of the rod, which is directly proportional to temperature difference at the ends of the rod. That is, H is directly proportional to Tc minus Td. Second one is directly proportional to cross-sectional area of the rod. That means H is directly proportional to A. Further, heat flow is directly proportional to time. During the heat flows through the conductor, okay? Directly proportional to time. That is, heat H is directly proportional to time T. And fourth one is inversely proportional to length of the rod. That means H is inversely proportional to L. Okay. Now, clubbing all these four equations, we can obtain what is thermal conductivity. Okay. Let us club all these things. Okay. Then that is heat flow H, which is directly proportional to Tc minus Td, directly proportional to A, directly proportional to time. Therefore, H is directly proportional to A, Tc minus Td into time T divided by the length L. Okay. Now let us replace this proportionality symbol. H is equal to some K A Tc minus Td into time T divided by length L, where K is a constant of proportionality, called constant of proportionality called thermal conductivity. Called thermal conductivity. Called thermal conductivity. Okay. So therefore you can rewrite this K by using this equation. K is equal to H into L divided by A into Tc minus Td into tan T. So this is the basic formula to calculate the thermal conductivity. K is equal to L by A of Tc minus Td into tan T. So by using this you can find the SI unit. So here SI unit of A is, say H is actually the heat flow that is measured in terms of joule. L is a length that is measured in terms of meter, whereas denominator we have area. Area is measured in terms of meter square. Therefore 1 meter and meter cancels out. The denominator meter is left, that take into the numerator, or meter power minus 1. Tc minus Td is actually the temperature difference that can be measured in terms of Kelvin. Take it to the numerator, that is Kelvin inverse, and tan is measured in terms of second. Take it to the numerator, that is second inverse. So joule, meter inverse, Kelvin inverse, second inverse with the SI unit of this particular thermal conductivity. Now see that the thermal conductivity, say if a material having higher value of thermal conductivity stands, it is quicker or faster to transfer the heat energy, or the heat energy transferred through that particular material with the high speed. So here you can consider thermal conductivity of some materials. Say K for the value of K for pure conductor is infinity. K for pure conductor is infinity. K for insulator, pure insulator, okay? Pure insulator is 0. Further you can consider some of the material. Say K solid is greater than K liquid. The thermal conductivity of solid is more compared to that of liquid, which is more compared to that of K gas. Okay, thermal conductivity of solid is always more compared to liquid, whereas liquid is more compared to gas. Some of the elements say K silver, which is greater than K copper, which is greater than K aluminium. So here the concept of thermal conductivity is more in the sense here the heat flow is fast. Okay, greater the value of K, quicker or faster. Quicker is the heat flow. Quicker is the heat flow. Okay. Now coming to the next point here related to this thermal conductivity is called temperature gradient. Okay. So this is actually the ratio of temperature between the ends of the conductor to the length of the conductor. Okay. The ratio of temperature difference. The ratio of temperature difference at the ends of the conductor, at the ends of the conductor to the length, length of the conductor is called as temperature gradient. Now this can be expressed in terms of temperature gradient is equal to Tc minus Td by L. Now from this equation Tc minus Td divided by L is equal to H by or Tc minus Td by L can also be expressed from this equation is H into L, H by Tc minus Td by H by Ka into T. So this shows that Tc minus Td by L is nothing but temperature gradient, or temperature gradient is inversely proportional to thermal conductivity K. See the relation between thermal conductivity and temperature gradient. Temperature gradient is inversely proportional to thermal conductivity K. Yes, let us come to the next concept here called heat current. So the term say current that you studied in the lower class also, because it is one of the familiar word. Current is actually the rate of flow of electric charges through a conductor, okay? But here we are going to discuss about heat current. That means heat energy flowing through the conductor. Then we can define the term say heat current as rate of flow of heat energy through the conductor. The rate of heat flow through the conductor is called heat current. Okay? Rate of heat flow through the conductor is called as heat current. So rate of heat flow is H by T. Now we already discussed about thermal conductivity concept where we can define H by T. H by T can be defined as Ka Tc minus Td divided by L. Correct? Ka Tc minus Td divided by L, because we consider H by T. Okay. So this is what the heat current formula. Now we can define, by using this heat current, we can define thermal resistance. Now it is a similar way what we studied in current concept, where we have electric current, electrical resistance, all that concept we are studying. Okay? Similarly here we have thermal resistance. Resistance is actually the opposition here. Okay? Now the heat flows through the conductor. If the conductor will oppose the flow of heat, then we can say that there is some resistance in the conductor. Okay? So therefore, thermal resistance is actually it is a phenomenon of opposition offered by the conductor to the flow of heat energy is called as thermal resistance. Okay? It is the opposition offered by the conductor to the flow of heat, energy, only current, only heat energy. Okay. Further, this can be defined as it is a ratio of temperature difference between the conductor, between the ends of the conductor, to the heat current. So normally electric current resistance we can define as it is the ratio of potential difference to the current flows. Ratio of potential difference to the current flow is nothing but normal resistance. But here the ratio of temperature difference between the ends of the conductor to the heat current is nothing but thermal resistance. That is, thermal resistance R is equal to temperature difference Tc minus Tb divided by heat current. Heat current is H by T. H by T. Or this can be expressed as R is equal to Tc minus Tb divided by what is H by T? Then we got here Ka Tc minus Tb divided by L. Divided by L. Now just see that this Tc minus Td cancels out. What is left here? R is equal to L by Ka. R is equal to L by Ka. So this is a formula for thermal resistance. R is equal to L by Ka is a formula for thermal resistance. Okay. We can also express like this. Temperature difference to the heat current is also nothing but thermal resistance. And this is another form of this equation by substituting these values here. R is equal to L by Ka. Now I can write what is the SI unit. SI unit of thermal resistance. SI unit of thermal resistance is, now see that here L stands for here length of the rod, okay? That is measured in terms of meter. A stands for cross sectional area, where we have meter square, okay? Meter square. But K is a thermal conductivity, that we know that, okay? So ಇಲ್ಲಿ meter square 1 meter ಮೇಲೆ ಹೋಗುತ್ತೆ, okay? ಒಂದು ಕ್ಯಾನ್ಸಲ್ ಆಗುತ್ತೆ, ಇನ್ನೊಂದು meter ಮೇಲೆ meter power -1 ಆಗುತ್ತೆ. But thermal conductivity K, that we know that is joule. That thermal conductivity K can be SI unit is, so it is L is in terms of meter divided by this is joule, because K is actually H heat energy into L at the meter, okay? HL divided by area meter square ಆಗಿ meter power -1 ಆಗುತ್ತೆ. Then temperature difference is Kelvin power -1, and then time is second power -1, okay? And here one more area is there. Area is actually meter square, okay? Meter square. Now this can be expressed as meter square cancel ಆಯಿತು. So what is left here? Kelvin second divided by joule, okay? So this is the final, that is equal to Kelvin second per joule is a SI unit of thermal resistance, okay? SI unit of thermal resistance. Okay, now we studied about temperature gradient, the relation between temperature gradient and the thermal conductivity came. Then we discussed about heat current. After that we discussed about thermal resistance, okay? Now let us apply all these concepts in series and parallel combination of rods. Now suppose if you connect two rods connected in series, the similar concept later next year you are also going to study in current also, where we are connecting two resistors in series, two resistors in parallel. Similarly here you can study the concept that you can consider two rods combination, series combination of rods, series combination of rods. We can consider two or more rods that may be connected end to end. Series combination means one end of the rod is connected to another end of the rod. Then that two rods are said to be in series. Okay? If we connect two rods in series, then what is the heat flow through that particular rod? first rod to second rod. Then what is the thermal resistance in series combination? What is the thermal conductivity in series combination? These things we have to calculate in series combination of rods. Okay. So consider two rods. Consider two rods of length L1 and L2. Two rods of length L1 and L2. Comma, area of cross section. Area of cross section A. That means both rods will have the same area of cross section. Later we will see that if we change the area of cross section, how we can rewrite all the formulas. Okay. Now let us consider both having same area of cross section and thermal conductivity and thermal conductivity K1 and K2 respectively connected in series. Connected in series as shown below. As shown below. That means here we consider two rods of different length. This is of length L1, another rod is of length L2. Area of cross section is A, both rods having same area of cross section with thermal conductivity is K1 and K2 connected end to end. See that this end of the conductor is connected to another end. Okay, this is called end to end connection, and this type of connections are called as series combination. Okay, series combination rod. You can later increase, instead of two rods, you can connect one more rod, 3, 4, and so on up to n number of rods you can connect like this. Okay. Now if you connect in series, then we have to calculate what is the thermal current. Okay, heat current. The first one is heat current. Heat current. Now see that heat current is actually the rate of heat flow through the conductor is called as heat current. Therefore, heat current at each and every point of this particular rod will be the same. Heat current at each and every point of the rod is same. So it is same in case of electrical current also, where if you connect two or more resistors in series, at every point on the circuit, if you calculate the current, we are getting the same current. That is in series combination. Okay. So here also heat current is same. Heat current is same in series combination. In series combination. That means you can consider here that is H1 by T is equal to H2 by T. H1 by T is equal to H2 by T. Okay. Now we know that what is H? H is the heat flow, correct? Heat flow. That H we can consider H is equal to K1 A1. Area of cross section is A. K1 A. Temperature difference. If you consider the temperature here is a T1, here is a T2 at the center and T3 at this point. Okay. If T1, T2, T3 the temperature at three different points, then K1A T1 minus T2 divided by the length L1 must be equal to K2A T2 minus T3 divided by L2. Okay, divided by L2. Now this is what the heat current formula. Now by knowing the known terms, you can calculate the unknown thing. Okay. Further, let us consider the resistance, thermal resistance. thermal resistance. Thermal resistance is actually in series, okay? Thermal resistance in series. Now, series combination Rs is equal to R1 plus R2. R1 plus R2, where R1 already we defined what is R, thermal resistance R. R is equal to L by Ka. Therefore, L is here the length L1. L1 by K1 into A plus L2 by K2 into K. Since area of cross section same ತೆಕೊಂಡಿದ್ದೇವೆ, therefore K1A, K2A. If there are different, then A1, A2 ಅಂತ ಬರೀಬೇಕು. Okay, this is the thermal resistance. Then thermal conductivity. Thermal conductivity, that is, we have the same formula I can use. Rs is equal to R1 plus R2, where Rs is, this is L1 plus L2 by Ks into area A is equal to L1 by K1A plus L2 by K2A. Okay, where we can define what is Ks, thermal conductivity. Ks is equal to, take this Ks to here, A will be cancelled, so Ks is equal to L1 plus L2 divided by L1 plus L2 by L1 by K1 plus L2 by K2. L1 by K1 plus L2 by K2. Okay, L1 by K1 plus L2 by K2. Now further, suppose if we consider this length, L1 is equal to L2, L1 is equal to L2 altogether, then what about Ks? Ks is equal to, this is 2L, this is L by K1 plus L by K2, L cancels, that becomes 2 K1 into K2 divided by K1 plus K2. Okay, so this is how we can calculate thermal conductivity in series combination. Okay, so we can calculate what is the heat current, what is the thermal resistance, and what is the thermal conductivity in series combination. Let us come to the another concept here, temperature interface in series combination of two or more rods. Okay, now let us see that here two rods of length L1 and L2 are connected in series. Two rods of length L1 and L2 are connected in series. Let T1 be the temperature of one end and T2 be the temperature of another end of the rod, and T be the interface temperature. When the two rods are in contact, the temperature is T. That we have to calculate. Okay, so that we can calculate by using the idea that in series combination, as we know that the heat current flowing through this particular conductor is same at each and every point. That means heat current in the first rod and second rod will be the same. So H1 by T is equal to H2 by T. H1 by T is equal to H2 by T. Heat current is same in both the rods. Or this we can express as H is equal to K1, because the thermal conductivity of this is K1. Area of cross section we consider as same A of T1 minus T. T1 minus T divided by the length of this conductor is L1, that is equal to this conductor, that is K2, thermal conductivity. Area of cross section is A. If area of cross section is different, then you can write A1 and A2. Okay, K2A of T minus T2 divided by L2. So this is the formula to calculate the interface temperature T. So here the value of K1, area of cross section, the value of T1, then L1, these are the known values and T is the unknown. Similarly here K2, A and T2 as well as L2 are known values and T is the unknown. Then you can, by substituting all these values, you can calculate what is the value of the unknown temperature T, or the temperature interface temperature T we can calculate. Let us see related to this concept or problem here. What is the temperature of the steel copper junction in steady state of the system, given that length of the steel rod is 15 centimeter, length of the copper rod is 10 centimeter, temperature of the furnace, that means here the two rods be connected in such a way that they are connected end to end, whereas one end of this rod is kept at say 300 degrees Celsius. This is the temperature of the furnace. It is kept at high temperature 300 degrees Celsius, whereas the other end is kept at 0 degrees Celsius. This is kept at 0 degrees Celsius. The length of this steel rod is 15 centimeter. This is of 15 centimeter, whereas the other one is copper rod is of 10 centimeter. Okay. Then area of cross section of the steel rod is twice that of the copper rod. That means steel rod is of larger area of cross section now. Steel rod is of larger area of cross section as compared to copper rod. Okay, area of cross section of steel rod is more compared to that of copper rod. That is 2 times of that. Okay, then thermal conductivity of steel is given as 50.2 joule second inverse meter inverse Kelvin inverse, whereas copper is 385 joule second inverse meter inverse and Kelvin inverse. Now let us use the idea here. The heat flow through this heat current in the steel rod is equal to heat current in the copper rod. You can just write the formula here. K1, that is K steel into area of steel rod of T1 minus T is equal to divided by L1 is equal to K copper, area of copper into T minus T2 divided by L2, where L1 is actually the length of the steel, L2 is the length of the copper rod. Okay, then I can substitute the values here. So to simplify this, let's just substitute Ks. K value for steel is 50.2 into area of cross section of steel is 2 times of that of copper, that is given there. Therefore 2 times of A, 2 times of A, that A and A will be cancelled out there. Okay, 2A of T1 is 300 degrees Celsius minus T divided by the length of this steel rod is 15 centimeter. Keep that in centimeter itself because other values are 7 centimeter or 15 10 power minus 2. Here this is copper. K copper is given as 385 into area of copper into T minus 0 whole divided by length of copper is 10 centimeter. This 10 power minus 2 cancels out. Area cancels out. Then if you simplify this, you can calculate what is the value of T. This is simple mathematical rearrangement. It gives 44.4 degrees Celsius. So this is for the temperature, interface temperature. Okay, temperature at the junction. Okay, here is 300 degrees Celsius. Here is 0 degrees Celsius. So temperature of the junction T is equal to 44.4 degrees Celsius. Let us come to the another concept here, the combination, the series combination we have discussed. Now let us connect two rods are in parallel. Okay, parallel combination of rods. Parallel combination of rods. Parallel combination of rods. Just consider two rods here, okay, of same length, okay. Consider two rods of same length L, two rods of same length L, area of cross section, A1 and A2. You can consider same area of cross section or different area of cross section, okay? A1 and A2, and thermal conductivity, K1 and K2 are connected in parallel as shown below. That means you have to consider two rods here. Two rods of thermal conductivity K1 and K2, area of cross section A1 and A2, they are of same length L, okay, and temperature at the two ends is T1 and T2. Temperature at this end is T1, whereas the another end is T2, okay. T1 and T2 be the temperature at the two ends of the rod. Then we can find some of the terms here like the heat current through this particular rod in parallel combination, and then you can calculate what is the thermal conductivity K, and also you can calculate what is the thermal resistance in parallel combination, okay. The first you can find heat current. In series combination also we calculate all these things, okay. Series combination, what we observed, heat flow or heat current is same in both the rods, okay. Heat current is same, but here in parallel combination, heat current is adds up, because they connected in parallel, heat current is adds up here. That means the heat current H is equal to H1 plus H2. Or you can write H by T is equal to H1 by T plus H2 by T. Or this is the parallel combination HP, or it is expressed in terms of say Kp, area of cross section is A1 plus A2 into T1 minus T2 divided by the length L is equal to H1 by T plus H2 by T. That is A1 of T1 minus T2 divided by L1 plus divided by L1 by L plus K2 A2 T1 minus T2 divided by L. This is how we can calculate the heat current, that is adds up, okay. Now we can calculate what is the thermal conductivity Kp. Thermal conductivity in parallel combination. From the above equation itself we can write Kp. K here L cancels out. T1 minus T2, T1 minus T2, T1 minus T2 cancels out. What is that then? Kp is equal to K1 A1 plus K2 A2 whole divided by A1 plus A2. K1 A1 plus K2 A2 whole divided by A1 plus A2. So this is the value of thermal conductivity. Then also you can calculate the thermal resistance. In parallel combination. So in general, in parallel combination, the resistance can be expressed as 1 by R or 1 by RP is equal to 1 by R1 plus 1 by R2. Series RS is equal to R1 plus R2. Parallel 1 by RP is equal to 1 by R1 plus 1 by R2. Therefore, here you can write 1 by RP is equal to 1 by R1 plus 1 by R2. Now I can substitute R1 and R2 values here. 1 by RP is equal to 1 by R1 is, that is L by Kp, okay? L1 by, we know the resistance, thermal resistance R is equal to L by Ka. L1 by K1A1 plus L1 plus L is 1 by L by K2A2. Okay, this will give us 1 by RP. Or in other words, RP is equal to, or RP is equal to L by K1A1 plus L by K2A2. So this is the final formula for RP, that is resistance in parallel combination. Okay. So this is the concept here: series combination of rods and parallel combination of rods. And a series and parallel combination of rods, you can calculate what is the heat current. Rate of heat flow is called as heat current, and then you can calculate what is the thermal conductivity in both the cases. Also you can calculate what is the thermal resistance. And in series combination you can also calculate one more extra point, that is called as temperature of interface or interface temperature. Okay. So this is a concept of conduction.